Okay, so your next homework assignment, no rest for you. Homework 2 is due a week from today. It's available now. It's maybe a little bit more practical than the first assignment, which had some kind of theoretical type questions. We're going to get more into application as the semester goes on, where it'll be less abstract and more actually applicable to professional design and practice. So this is heading in that direction. So have a look at that assignment, get an early start. You'll be able to get pretty well through some of the problems just based on what we do today as far as examples and lecture. What we're going to be doing is moving into Chapter 8 in the textbook, and we're going to be discussing some more sophisticated ways of estimating friction factor besides using the Moody diagram. And then we'll apply that to an iterative design process meant to size pipe diameter. Any questions before we move on? All right. Moody diagram. You've seen it, you've used it, you know it. We use the Moody diagram in order to identify the friction factor, F. Now, the Darcy-Weisbach equation is what we use to estimate the effect of pipe friction. So if we're using the energy equation, and I'll write it on the board because we're going to refer to the energy equation a couple of times today. The pressure head plus the elevation head plus the velocity head plus, if there is a pump, H sub P is on the left-hand side of the equation, is equal to, for the right-hand side of the equation, the pressure head, elevation head, velocity head at 2, plus the head loss due to pipe friction, plus the head loss due to local losses. And collectively, we sometimes combine these together and say that they are the head losses. So in the energy equation, the trickiest thing often for us is estimating the effect of pipe friction. And what makes it tricky is that even for the same kind of pipe, if the water is moving slowly, there will be a completely different friction effect that applies compared to if the water is moving quickly through the same conduit. So that difficulty in estimating the friction factor largely falls into the challenge with calculating F, the friction factor in the Darcy-Weisbach equation. So we saw in the Moody diagram that there's a section where the F value really only depends on the relative roughness. When we're in this rough turbulent zone, you'd have the same friction factor if the Reynolds number is 10 to the 6th as you would if the Reynolds number is 10 to the 7th. See how this line is flat? What that's implying is that there's a certain threshold beyond which additional increases in Reynolds number isn't changing the friction factor at all. That's the rough turbulent zone. On the left-hand side of this dashed line, in the transition zone, is where the Reynolds number and also the relative roughness come into play for determining the friction factor. So the Moody diagram is useful, but the weakness of using a figure for estimating F instead of having some formula is that it's imprecise. And so, you know, how straight your ruler is or how thick your pencil lead is as you're trying to lay down a line and reflect it off of the curve. There's just some imprecision there that you can chalk up to user error or differences in visual acuity or whatever. So it's subject to some imprecision because of differences in how people read the figure. But then also, if we want to iterate, like if we want to do calculations really quickly, then it would be a nuisance to have to go back to the figure anytime we have a different Reynolds number and kind of manually interact with the figure when there might be a formula that would allow us to automate that process. And so there is. We don't have to rely on the Moody diagram. The Colebrook equation is kind of the gold standard for estimating the F value anytime the Reynolds number is greater than 2,000. If the Reynolds number is less than 2,000, estimating the Reynolds number is, estimating the F value is simple because it's just a function of the Reynolds number. And in fact, that formula is on the Moody diagram. If you see this little curve here, if you have laminar flow, which is almost never. So that's why we won't dwell on it too much, is laminar conditions are very, very rare. Water has to be moving at just a snail's pace through a pipe for laminar conditions to apply. In any kind of service condition, you'll have turbulent flow in the pipe. But just to know it, the friction factor can be estimated very easily if you have the Reynolds number 2000 or below. Okay, so beyond that, the Colebrook equation is the gold standard, and here's the Colebrook equation. What you'll notice, if we're trying to solve for F, is that F is both on the left-hand side of the equation and also on the right-hand side of the equation. So this function is tricky to use for that reason. The F value is both on the left and it's both on the right, and it's not that someone's just been lazy and not bothered to algebraically isolate that F value. It can't be. It belongs on both sides of the equation. And so this is an implicit equation. And for us to use it, we have to iterate. We have to begin with some guess value of F and check the left-hand side and the right-hand side and see if it balances, and if not, we change our guess, and eventually we can find the F value that applies using the Colebrook equation. But you need a good calculator or a computer, and I was going to bring a good calculator to show you what it looks like. You know, like the big TI graphing calculators are okay. A Hewlett-Packard graphing calculator is really good, but it's difficult to solve the Colebrook equation, if not impossible, with the Casio calculator. You can use Excel, but I don't know if Casio has the processing horsepower, or maybe you don't have the patience for it to converge on the solution for the Colebrook equation. Okay, now the two things I want to point out inside of the parentheses. Think back to the Moody diagram, that there's a region where the Reynolds number doesn't matter, and what really matters is the relative roughness. And then there's a region where both the Reynolds number and the relative roughness matter. So there's two terms inside of here, a relative roughness term, K sub S to D, and then there's a term where the Reynolds number applies. And so it's tightly related to those two different zones on the Moody diagram. If you have a big Reynolds number and this term is in the denominator, as Reynolds number goes to 10 to the 7th, 10 to the 8th, 10 to the 9th, then since it's in the denominator, this second term is going to become inconsequential, and all that matters is the left term inside the parentheses there. So this K sub S to D is the relative roughness, where K sub S is the equivalent sand roughness we've talked about before. We've seen a different table. Here's the table that's provided in your fluid mechanics book of different equivalent sand roughnesses for pipe materials. Sometimes K sub S is used. Other texts and equation books use epsilon as the variable for that. But the idea is that you'd have some indication of how rough the pipe is. So if you compare, for example, brass tubing, which is pretty smooth, has a very low K sub S, compared to a cast iron pipe, which is relatively more coarse as a material, has more pipe roughness, and the K sub S consequently is much higher. Okay, so let's get a feel for how to use the Colebrook equation, and I'll show you how to apply Microsoft Excel for determining the friction factor that should apply in this condition. We've got galvanized iron, so we could go to that table and find the K sub S for galvanized iron is 0.15, and we've got 200 liters per second flowing through a pipe that's got a diameter of 136 millimeters. And so inside the Colebrook equation, you can see here's the Reynolds number, and just to refresh your memory, here's the formula for Reynolds number in terms of kinematic viscosity. But let's determine, for these flow conditions, what is the Reynolds number. Then we'll fire up Excel and do that iterative process of solving the Colebrook equation. So if the diameter is 0.136 meters, then the area will be pi d squared divided by 4. Okay, so the cross-sectional area of this pipe is 0.01453 square meters. That's the cross-sectional area of the pipe, and the velocity of the water that flows through it is the flow rate divided by the cross-sectional area. So V equals Q divided by A. So our flow rate is 200 liters per second. Does anybody know what that is in terms of cubic meters per second? 0.2. Good. Because there is 1,000 liters in a cubic meter. So the exchange between liters and cubic meters should be instantaneous in your mind. Just divide by 1,000 if it's liters per second. So our flow rate is 0.2 cubic meters per second. Our cross-sectional area is 0.01453 meters squared. That gives us a velocity here of 13.77 meters per second. Now this is an extreme example. That's really fast. So water's moving through this pipe at quite a clip, much faster than it would in any kind of municipal application. Normally you wouldn't see flow of more than 3 meters per second inside of a typical municipal pipe, because there's going to be so much friction loss when you've got flows that high. But let's find out for a Reynolds number. Reynolds number is velocity times diameter divided by kinematic viscosity. Our velocity 13.77 meters per second. Our diameter 0.136 meters. And the kinematic viscosity 1 times 10 to the minus 6th meters squared per second. So if you put that into your calculator, I think what you'll find is that the Reynolds number is 1,872,413. So 1.8 times 10 to the 6th. Okay, so I'm just going to start with a blank workbook in Excel. This isn't yet the template file that I was mentioning. We're just starting with a blank workbook here. And we're going to, I'll paste the formula just so it's there for me to see and refer to as we set up how to solve this. All right, so we're going to put in the K sub S of the pipe is 0.15 millimeters. I'll put the units off to the right there. The diameter of the pipe is 136 millimeters. And note that if you've got a ratio, see this formula here, K sub S divided by 3.7D, the units need to be the same. So either both K sub S and D should be in meters, or both of them should be in millimeters. But I can't use mixed units and expect a reasonable answer. So I'm going to do it as millimeters, but you could put meters, and as long as you were consistent in that ratio, it would be all right. The Reynolds number we got was 1,872,413 is our Reynolds number. Okay, I'm going to have 3 columns here. The guess F value as one column. I'm going to have the left-hand side of the formula and the right-hand side of the formula, and I guess I'll put in a fourth because I want to calculate the difference between left-hand side and right-hand side. Okay, so let's just check on the Moody diagram. What's the typical range? I know you had a homework problem where you calculated an F value of like, what was it, 0.9 or something, when you were finding the F value equivalent for this open channel. We don't use the Darcy-Weisbach equation for open channel flow much, so that was kind of an odd application. For closed conduit flow, the typical range of friction factor would be starting at 0.008 and going through 0.038. So that's what I'm going to do here, 0.008, 0.009, and then I'm just going to have it continue onward until we get to 0.0038. And we're going to see, is the left-hand side and the right-hand side equal for some guess value of f? Because I don't know what the f value is. I could solve for it if I had my HP calculator here, but I don't have it with me right now. Okay, so the left-hand side equals, equals 1 divided by square root of f. Okay? Did I do something wrong there? Okay, I guess. Oh, yeah, it's referring to the wrong one. Let me just, A6. Yes. Okay. So we just did the, it's very strange. Where I'm clicking, the mouse isn't going where I'm clicking. It's going to be confusing. All right, so just the left-hand side of this formula is the square root of, the inverse of the square root of the f value. Okay, right-hand side, this is going to be a little more complicated to type in the formula here. So equals -2 times the log, parentheses. Okay, so I want to refer to the k sub s, and so I'm just going to click on the cell there, B1, and then what button do you push to lock a reference to B1 with the dollar signs? F4, good. So by pressing F4 on the keyboard, now I've got $B, $1, and that means that when I drag the formula down into other rows, it's still always going to look up there at k sub s, because regardless of which row I'm on, the relative roughness of the pipe stays the same. Okay, so that's the k sub s. Now divided by 3.7 times d. And so I'm going to click on the reference to d and put the lock in by pressing F4. All right, so now I've got the first term. Once I close parentheses here, I've got the first term inside the parentheses. Now I'm going to add the second term, so plus, oh, I need to do another set of parentheses, I think. Okay, so plus 2.51 divided by the Reynolds number, anchor the reference, times the square root of the f value. Okay, now close the parentheses for the f value, close it for the denominator, and finally close this parentheses that was around the logarithm. And I think there's one more. All right. I regret that that's not bigger, but hopefully you can see that. And what we get is that the right-hand side of the equation and the left-hand side of the equation aren't the same. So there's a difference there. It doesn't matter if I do left minus right or right minus left. I'll just do left minus the right. What I'm looking for is I'm looking for what f value is going to make the difference equal to 0. And then when I know that I've found the f value that makes the difference equal to 0, then that's the f value that applies for this pipe scenario. So what I can do is I can click and drag downward through all of the different guesses of f value for the left-hand side formula. I can click and drag downward for the right-hand side formula. And in fact, you don't actually have to drag. You can just double-click. See that kind of thicker green arrow here in the bottom right-hand corner? If I just double-click, it'll take it down through the bottom. Question?
I think everything that second parenthesis you have right after the first division sign is putting everything underneath KS.
Let's see.
Yeah, because it's a little sad I didn't get it right hand side.
Okay. Yeah. I think you're right. Thank you for catching that. You are absolutely right. I had one too many parentheses sign. Good catch. All right. So I'm going to need to adjust that all the way down through. Okay. Very good. So, when in doubt, throw it out. Let me just double check that I've got the right thing here. So, -2 times the log of k sub s anchored divided by... Now, let me show you a little trick. We don't actually need the parentheses. We could do divided by 3.7 divided by d. And so that's the same as if you'd had the parentheses and had the 3.7 times d. It's just basically we're dividing both 3.7 and the d by the k sub s. Plus 2.51 divided by the Reynolds number divided by the square root of the f value. So maybe I'll get into less trouble if I have fewer parentheses and I use that divided by trick instead. And let me just drag that through. The numbers won't change, but, well, if I anchor the references correctly, the numbers won't change, which, let me do that here. All right. Okay, so now, with that fixed, thank you again for catching it, let's subtract the left-hand side and the right-hand side all the way down through, and what we'll find is that there's this crossover point. Somewhere between 0.02 and 0.021, the difference goes to 0. So that tells me that the f value is between 0.2 and 0.21. Well, what I want to do is I want to have the difference equal to 0. Does anybody know of a good tool within Excel that would allow me to go the rest of the way? Goal-seek, yeah. So here under Data, What If Analysis, Goal-seek, I'm going to tell it that I want the difference to be equal to 0. So I did the value in cell D18. I'm looking for a goal of 0, and I'm giving permission to Excel to change A18, which is where the f value for that row is found. And so it will go, and if I just show a little bit more precision here in my digits, 0.02027. So that is the f value that applies in these conditions. So it's more precise than a Moody diagram could be, but it's certainly not more convenient. So you're probably not sold on the Colebrook equation. I mean, when accuracy counts, maybe go through the trouble, but luckily there's a more convenient solution than Colebrook. Before we move on to discussing the Colebrook equation, any questions about the example? Colebrook accurate, but a little bit tedious to use. There's a video on my YouTube channel if you want to see how it can be solved directly using the HP50 calculator. I'll invite you to check that out. I think that in the notes this remains as a hot link, or you can just search HP50G calculator on YouTube on my channel and you'll find that video. I just show you basically how to solve an implicit equation by setting up the equation writer. But the more convenient approach to estimating the f value is the Jain equation. And I just said estimating the f value. It's not a absolutely correct in every flow condition calculation of the f value, but it's a pretty good estimate within certain boundaries. The Jain equation works as long as the relative roughness is between 10 to the minus 6th and 10 to the minus 2nd, and then between the flow range of Reynolds number above 5,000 but less than 10 to the 8th. That's a pretty good range. That's a broadly applicable formula. And in some ways it looks similar to the Colebrook equation because we have a logarithm. In this case it's natural log instead of the base 10 log that we saw for Colebrook. But there's a logarithm inside of which is a relative roughness term and then a term which is dependent on the flow conditions and the Reynolds number. But the beauty of the Jain equation is that f values just by itself on the left-hand side. And we could set this up in Excel a lot easier. You could set it up on paper a lot easier than Colebrook equation. So this semester, unless you are told to use the Colebrook equation, you can use the Jain equation. It's good enough and applicable enough over a broad range of conditions that the Jain equation is okay. So in our previous example that we were just testing out the Colebrook, you got a K sub S of 0.15, a diameter of 136, the Reynolds number of 1.8 times 10 to the 6th. So what is the F value? Let me pause for a second and let you calculate the F value, because we know if you use the gold standard, it should be 0.02027. Let me write that on the board so we've got it as a reference. And I'd like you to try calculating the Jain equation to see how closely it matches. Colebrook. Jain. All right. Here's the formula. You've got all the variables, so calculate F. In hydraulics, and especially hydrology, if you ever get into hydrology, then you have to be comfortable with a little bit of uncertainty. But oh yeah, okay, so I guess the actual Reynolds number that we had from the other example was 413, right? So I don't know how much, since this was already 1, 2, 3, 4 digits, that may have an effect.
02024.
It changes this to 24? Okay.
I still got 318.
You got 318 by changing that?
413,
All right. So the Jain equation, we use it to estimate the F value. There's one called the Blasius equation, which is valid for a Reynolds number up to 100,000, and it's pretty simple to apply. But you won't hear about the Blasius equation very often, but I wanted to make you aware of it. Okay, moving on into some application. Sometimes we want to know how big of a pipe we should use. If you use a big pipe, then it's going to cost your client a lot of money, because obviously large diameter pipe uses more material, which has a higher cost than a small diameter pipe. But what are you getting when you spend the extra money? Like if you use a large diameter pipe, then the water travels through the pipe at a lower velocity. There's less head loss due to pipe friction, you lose less energy, and the pressure is better downstream. That's exactly the same thing of what I was telling you on the first day of class, how the plumber at my house was suggesting a 1/2-inch pipe. I ended up going with a 1-inch pipe so that I can have every tap open and still have good water pressure. So in this situation, if you had a building and you're trying to have water flow from an elevated storage tank, and if you know that a certain amount of energy loss due to pipe friction is acceptable, so if H sub F is known, then you may try to estimate what is the diameter of the pipe that's required for that. Now this equation, I've just rearranged the energy equation and solved for H sub F. I had that on the board earlier. If there's no pump term, and if we neglect the velocity head. Velocity heads are usually very small component of where the energy is. The energy is most typically tied up as pressure head and elevation head. And so in some calculations it's customary just to eliminate velocity head, especially if at 1 and 2 the velocities are approximately the same. But let's say that you know the flow rate that you're trying to get to this building downstream, and you know how much energy loss is acceptable. And so the thing that we're trying to calculate then would be the pipe diameter and the material type that would allow the required pressure downstream to be supplied. So that's the thing you're designing. You're designing how big should the pipe diameter be. of course, the difference between design and analysis is often that design is iterative, that you have to keep changing parameters around in order to meet some established criteria. So the criteria could be how much pressure is needed at the building, and the iterative process change of adjustment and check, adjustment and check. The iteration there would be trying out different diameters. Now, why would iteration be required? It's because if you have a big diameter, then the velocity is lower. And if the velocity is lower, the Reynolds number is lower, and the F value depends on the Reynolds number. So as you change D, you also change the F value. If you make the diameter of a pipe smaller, then that forces for a given flow rate, the velocity will be moving more quickly through a pipe. High velocity means high Reynolds number, and therefore there's going to be a different friction factor that applies for the same flow rate and the same pipe material, different friction factor depending on which diameter you use. So the tricky thing about this whole question of how big should the pipe diameter be, the tricky thing is that the F value changes anytime you change the diameter. So we could take the Darcy-Weisbach equation and rearrange it to solve for what diameter is needed for a circular pipe if we know the head loss that's allowable, we know the length of the pipe that's between 2 points, we know the flow rate that needs to be provided, but this friction factor is going to be constantly changing. And that's why we have to do this iterative calculations on Excel. F isn't constant because it depends on the flow rate, relative roughness, and the velocity. All right, so the most accurate way to estimate the diameter that's needed is an iterative process. And what we will do to begin this is we're just going to guess an F value to begin. So you'll start with some assumed F value because you don't actually know what's the F value when you begin your calculations because you don't know what's the velocity through the pipe. You don't know what diameter you're using yet necessarily. So you have to start with a guess, and then you'll converge on the right answer and you'll improve your guess along the way. But our step here is somewhere within this range of typical F values. We'll begin with a guess, and then with that guess F value, we'll determine what diameter of the pipe is needed for this length that we know, for the flow rate, and for the head loss that can be tolerated. Once we know the diameter, you can calculate the Reynolds number, and with the Reynolds number and the equivalent sand roughness and the pipe diameter, then you can find an updated F value with either the Colebrook equation or the Jain equation, or maybe even a Moody diagram. You just have an updated F value, but then you have to recalculate the diameter again because you have an improved guess of what the F value was, and previously you were just guessing of an F value out of thin air. You were just picking an F value. And so you repeat this process as many times as necessary until the new F value agrees with what you've assumed in a previous iteration. So it's the process of calculating until you achieve convergence. So we're going to apply this process to the following example, where we have a main pipeline that we're tapping into, and we've got a lateral pipe that's taking water to a house. And I guess we know at this house we want there to be 300 liters per second coming out of the tap. We want to try and figure out, maybe it's not a house, that's a lot of water. Let's call it a factory. So we're trying to take water a distance of 40 meters through some pipe, and what we're going to do is we're going to say that 45 meters of head loss is acceptable. That's how much energy we can afford to lose as the water flows through that pipe. We're going to guess an F value, and from the guess we'll calculate an initial diameter, we'll calculate the flow velocity and therefore the Reynolds number, we'll calculate the equivalent sand roughness and to the diameter, so that's the relative roughness, and use those things with the Jain equation to find an updated F value, and then we'll do the process over again to find out what is the new diameter that's needed with that updated F value. So we'll just repeat this process over and over again until the F value isn't changing anymore. Okay, so open up that file, the pipe diameter needed file that you can find on Blackboard. If you don't have your computer or if you don't want to follow along, that's okay. No problem, just watch. That file is there and you can go through this anytime. The video is going to be on Excel, so if I jump over some step too quickly, you can find it later. All right, so in the example, our flow rate is 300 liters per second. So that is 0.3 cubic meters per second. The pipe is said to be cast iron with a K sub S. Here I've got units of meters specified. So the K sub S is 0.26 millimeters divided by 1,000 millimeters per meter. So 0.00026 is the equivalent sand roughness. The pipe length is 40 meters. G we know is 9.81 meters per second squared. The energy loss that can be tolerated through this 40 meter length segment of pipe, we can allow there to be up to 45 meters of head loss. And then the kinematic viscosity of water is 1 E minus 6. So 1 times 10 to the minus 6th. Any questions so far? We're just basically translating the problem statement here into the spreadsheet. Okay, so we're going to start with the guess value of F. And just to illustrate that no matter how bad your initial guess is, you can get it to converge on the right answer. I'm going to have the smallest F value that's possible, 0.0008. So that's at the low end of the scale. No, that's one too many zeros. 0.008. Yeah. All right. So we're going to use this formula now to estimate what diameter is needed for this guess value of F. Okay, so it is, I'm putting in a parentheses here, first of all, 8 times the length. So I'm going to click on the cell that has the length in it, and I'll anchor the reference, times the flow rate. Here's the flow rate, B4, anchor that reference, and I need to square the flow rate, divided by, well actually I'm also multiplying by the F value. So let me do that before I begin my dividing. F is in the numerator. So times F. Now I'm not anchoring that reference intentionally because I'm going to paste this formula down below and I want it to look at the updated version of the F value. So I'm not anchoring the reference to F, but I did anchor the reference to flow rate and length. Divided by H sub F, anchor that up in the top, times G, anchored, times pi squared, pi, close parentheses, squared. And then I need to close the parentheses for the denominator, close parentheses for the expression in these big parentheses here, and then I take it to the power of 1/5. So that's basically to the 0.2 power. So under these conditions, if the F value was 0.008, then the diameter of pipe that I need should be 0.1395 meters. Okay? So if that was the diameter, then what's the flow velocity? Okay, so the flow rate I know is 0.3. The area, I'm going to do it based on this guess of the diameter. So area is pi times d squared divided by 4. So that's the area of a pipe that has a diameter of 0.1395. And the velocity is the flow rate divided by the area. So the water would be moving at a velocity of 19.6 meters per second if the diameter is that small. Okay, and now if that's the velocity, what is the Reynolds number? The Reynolds number is the velocity times the diameter divided by the kinematic viscosity of water. I need to anchor the reference up there to the kinematic viscosity so it'll always stay the same. So 2.74 times 10 to the minus 6, 10 to the 6th. Now, let's improve our guess of the F value using the Jain equation. So we have a Reynolds number. We can do better than just picking an F value out of thin air like I did at first. Let's get a newly updated F value using the Jain equation. So equals, you're going to get good at typing the Jain equation this semester, 1.325 divided by the logarithm of k sub s, which was here. I'll anchor that reference, divided by 3.7 divided by the diameter here within this iteration, plus 5.74 divided by the Reynolds number to the power of 0.9, and then all of that is squared. So the point is we have a newly updated F value that we got from the Jain equation, and the difference between the old one and the new one is pretty big. So for a percent difference, I'm going to have new minus old divided by new. So new minus old divided by new times 100. So it changed by 65%. Our solution is not yet iterated, not even close. So iteration 2 is going to be a little bit easier because in iteration 2, I'm going to use my new F value that I just got. So this new F value, boy, this is so strange. I click on a cell and the numbers are showing up in the wrong spot. All right, equals this F value. Okay, so using this previous one, now I'm just going to copy this formula and I'm going to paste it in the location. So Control C, I'm not going to type the formula over again. I'm going to paste the formula. And I have this newly updated value of diameter. And then the same thing, I'm going to copy all of this, Control C. I'm going to paste it down here, Control V. Control copy and paste it. I'm having some kind of a problem here. I guess what I need to do is probably lock the reference here to the, I need to lock the reference to the flow rate. The others I don't, though. That's what it was. All right, Control C. That's more like it. So I have, for the flow rate that we know, this is going to now look at the new diameter for the area. We have a new guess of velocity, a new Reynolds number, and then I can use this function here, Control C, and I can just paste in the newly updated F value as well. Okay, so I'm going to save it. I don't want to keep you late. I'm going to save it, and we're going to begin our class on Friday by revisiting the rest of this example. Just to finalize, remember that the homework assignment that's due next week is available now for you to begin on, so I'd encourage you to have an early look on that. See you Friday.
Is there any problems that we went over today on the homework?
What's that?
Can we go ahead and start?
Yeah.
Start completing problems?
Yeah. The first problem is to use the Colebrook equation. The second problem is use the Jain equation. Yeah. So you can get started.
Can we use
know what?
Excel on the homework?
Yeah.
I don't like any of you.
You can.
I know what's up with me.
I'll just make sure we submit our files, submit our scan.
Yeah.